The algebra of angular momentum, which is also related to SO3, to the group SO3, the special orthogonal group in 3 dimensions, can also be derived from a path integral. And that's what I would like to show in this quick video. I have prepared a PDF with all the necessary equations, and I would just like to go through this PDF quickly, but if necessary, of course, I can give you the PDF version so that you can try to follow it more slowly and you can go through the derivations. But let's start from the fact that we want to arrive at the algebra of angular momentum, so SO3, the special orthogonal group of in 3 dimensions, and we will start our description from a unit vector n of t, which lies on the sphere. In particular, we want to impose the fact that the magnitude of this vector is equal to 1. And its orientation is general, so it can be in any kind of orientation. The tip of the vector lies on the sphere, so it can be in any kind of orientation, let's say. And we can define the classical angular momentum as a vector capital S equal to little s times this unit vector n. So basically the parameter s is just the magnitude of the vector capital S, and n is the direction of the vector s. So we are, in this case, interested in the direction of this vector, assuming that the magnitude little s is fixed. So we want to describe the dynamics on the unit sphere using the following Lagrangian that we will explain in a moment. So the Lagrangian can be written as little s, which is the magnitude, and this is just a constant in our case, so this is not the important part. The important part is this. So we have phi dot times 1 minus cosine theta. So phi and theta are the usual parameters that we use in spherical coordinates. So in particular, theta is the polar angle, whereas phi is the other angle on the y axis when you consider spherical coordinates. And this Lagrangian here is related to the time derivative of a small area on the unit sphere described by the vector capital S. So let me explain it. In particular, we want to consider the infinitesimal area, dA, equal to 1 minus cosine theta times d phi. So as you can see, if you multiply this Lagrangian by the infinitesimal time dt, we have phi dot, which is d phi over dt, so we get d phi, right? So this is an infinitesimal area. Basically, it is just the Lagrangian multiplied by dt divided by s, but s is not important, it's just a constant in this case. And this is a two-dimensional surface on the sphere. And why? Well, the surface element on a unit sphere in spherical coordinates is the following. So we have sine theta, d theta, d phi. So it is just a small element on the sphere. And we are going to integrate over theta. So we can integrate over theta from a generic, so from 0 to a generic theta. So we have something like sine theta prime d theta prime, and then we integrate from 0 to theta. And what we get is 1 minus cosine theta. So we carry out one integration over theta. We still have an infinitesimal angle phi there. Phi and theta are the usual spherical coordinates, as I said. Therefore, you can understand why we can consider a Lagrangian of this form, starting from an infinitesimal area. So that's the intuition. And we define the path integral like this. So we have the Lagrangian multiplied by I over h bar. And of course, you have to integrate over dt. And you put that inside the exponential in the path integral. And then we also want to impose the fact that the vector n is unitary. So we can put this delta, Dirac delta, for example, inside the path integral, and then we can indicate the path integral like this. So the path integral is performed over the vector n of t. So we are imposing the condition that n is unitary, and then we have a Lagrangian of this kind here. So that should be a little bit intuitive, hopefully. Now, the term inside the integral is analogous to the classical expression pq dot. So if you consider a particle, a generic particle also in one dimension, for example, to consider a simple case. And pq dot is the momentum of the particle multiplied by the derivative with respect to time of the position of the particle. So pq dot, if you remember, appears in the Hamiltonian of the particle, just to remind you of that. And in our case, instead of having pq dot, we can consider p sub phi times phi dot. And we can define p phi as s times 1 minus cosine theta, and that appears inside this Lagrangian. It appears in the Lagrangian. So we have phi dot multiplied by p phi, and we can identify the canonical pair p phi times phi. So when we consider canonical quantization using the path integral, the term pq dot leads to the well-known commutation relation between the position of the particle and momentum. So the commutation relation between the position and momentum of the particle is equal to I h bar, right? Where h bar is the usual reduced Planck constant, and I is the usual imaginary unit. So that's the usual commutation relation that we have in quantum mechanics. Now, in our case, we have to replace q with the position that in the specific case of angular momentum is simply phi, whereas the momentum p is replaced by p sub phi. We defined earlier this p phi here as times 1 minus cosine theta. So p phi is a function of theta, and we have this commutation relation basically. So we have the commutation relation between phi and p phi equal to I h bar. Now we define the so-called spin or angular momentum components if you want. So we have s sub x equal to s times sine theta sine phi, s sub y equal to s times sine theta cos phi, and s sub z equal to s cosine theta. So basically it's the same vector that we had defined in here, but we rewrite it in polar coordinates. And what we want to do is we want to compute the so-called Poisson brackets that we have, for example, in classical mechanics, and then we quantize it using the following statement. So we convert the Poisson brackets multiplied by I h bar to a commutator, right? Or if you want, the Poisson bracket is replaced by the commutator divided by I h bar. So we want to compute the Poisson brackets. For example, the Poisson bracket between phi and p phi, using the definition of the Poisson bracket, is simply equal to 1. So we multiply by I h bar the Poisson bracket, and we get the commutator. Indeed, we get this one. And that's what we want to, that's what we indeed get also from the path integral. And now we can calculate, for example, also the commutator between sx and sy. Right? So we have to compute the derivatives. This is just a calculus exercise. In particular, we want to calculate the derivative of sx with respect to phi. And if you do that, you get this expression. Similarly, you can calculate the derivative of sx with respect to p phi. And we can rewrite that by decomposing the derivative like this, using the chain rule. But since p phi does not depend on phi, basically the term that we have here on the right is 0. And we only have this term on the left, this one. And the derivative of theta with respect to p phi can be calculated basically and informally by taking the derivative of p phi with respect to theta, and then you take the inverse of that. So you raise that to the power minus 1, and you will get 1 over s sine theta, for example. So you can put the results together also for s sub y. You can do the calculation. In particular, this is how you compute the Poisson bracket in classical physics, and it's the same Poisson bracket that we calculated earlier. But in the case of phi and p phi, that's very simple. In this case, you have to go through a little bit of a calculation, and what you get is s cosine theta for this Poisson bracket, but that's equal to s sub z. And s sub z, indeed, if you check these definitions here, is s cosine theta. So you get that the Poisson bracket between sx and sy is equal to sz. And when you convert this to a commutator, you get the commutator between sx and sy equal to I h bar Sz. Similarly, you can compute the Poisson brackets for Sy, Sz, Sz, Sx, and you will get these obvious results, quite obvious. That's the result that you should expect. Because indeed we get the classical SO3 Lie algebra. So we get the algebra of angular momentum, basically the algebra of rotations in three dimensions, and that's the algebra of the special orthogonal group SO3. And this exactly gives the spin commutation relations, or if you want, the angular momentum relations. And this is something that I wanted to show you because, in particular, we see that also from the perspective of path integrals. And this is not so obvious, this is not shown in ordinary courses because this is quite advanced. And actually, if you want, let me conclude this video by saying this statement without getting into the details. We have considered a path integral related to some kind of area. So basically, it's like discretizing or quantizing, if you want, areas. And this is also what happens, for example, in a theory like loop quantum gravity. In loop quantum gravity, indeed, we have the algebra of SU2, and that algebra is still related, of course, to SO3 because SU2 and SO3 are related. I will not get into that detail, but it's also quite intuitive if you study special unitary group in 2 dimensions and the special orthogonal group in 3 dimensions, thinking also of, for example, polymatrices. Well, in loop quantum gravity, you have the algebra of SU2, and that's used to discretize, to quantize, to be more precise, areas. And I will conclude the video in here.